So my name is Brendan Hassett. I'm a professor of mathematics at Brown University, and I'm the director of ICERM. ICERM is the Institute for Computational Experimental Research in Mathematics. We're funded by the National Science Foundation, Division of Mathematical Sciences, the Simons Foundation, and other individuals and sponsors to support mathematical sciences collaboration, conversations, and education. So normally, before the pandemic, we would bring people from all over the world to Providence to talk about math and to find new math to collaborate on. We're really interested at the nexus between math and computation, cases where mathematical results will lead to new algorithms and new computational techniques, but also using computers as a laboratory to figure out what might be true from a mathematical perspective. So we have a number of public lectures, normally held in person, but during the pandemic, we've discovered the value of virtual public lectures. And so we're really pleased to host Ranthony Edmonds to do the second public lecture of the summer. So she works in commutative ring theory, which is the study of factorizations. And so I think many of you know that if you take 6, you can multiply it by, express it as a 2 times 3. But factorization is really an intricate and beautiful part of mathematics. And speaking as a fellow algebra aficionado, it's one of the most beautiful areas that one can study. Ranthony does a lot of fundamental research in this area in terms of when factorizations exist and what properties that they have. So she works at Ohio State University as part of a research training group in topology and its applications. So she has previously worked as a doctoral student at the University of Iowa and has done a master's degree at the Eastern Kentucky, and her bachelor work was at the University of Kentucky. She has designed a really innovative course on intersections of mathematics and society, hidden figures. And so she's already emerged as a leading expert of how mathematics and issues in the larger society interact with each other. And this is a really important focus for our public lectures. So Katie, is there anything else that you'd like to say? We sort of scrambled our plans for the introductions, but.
No problem at all. I'm delighted with that. I'm delighted to have Ranthony here.
Yeah, so let me hand it over to Ranthony. Thanks very much.
Thank you so much for that introduction. So I'm going to go ahead and share my screen. So I'm excited that we're able to connect, albeit virtually. I'm really excited about the Girls Get Math program. It just sounds so wonderful. I wish I had known about these sorts of programs when I was younger. Let's see. So let's go ahead and press present. Okay, so can everybody see my screen?
Yes.
Okay, great. So thank you so much for introducing me again. It's a pleasure to be here. Thank you guys so much for joining. I'm excited about tonight. So just to reiterate, my name is Ranthony Edmonds. I am a postdoctoral scholar at The Ohio State University. We take the very seriously here in Columbus. And as was mentioned, I study factorization theory and commutative rings. I'm doing a research transition into applications of algebraic topology, really interested in electoral redistricting, but I'm also really interested about who is a part of the mathematical community, whose stories we tell, and trying to encourage more people to participate in mathematics, because like I said, it's a beautiful discipline. I want everyone to be able to participate. So the way that I've sort of done this is through storytelling. So tonight, rather than give sort of maybe a traditional research talk, I want to talk about how storytelling and amplifying hidden narratives in mathematics has really led me on many different adventures in my teaching and also in my research. So I wanted to just start with a basic question, which is, why should we care about storytelling in mathematics? And it looks like, let's see. So I kind of wanted to put this to the audience and read from the chat. I'm not sure if I'll be able to see what anyone writes. So if I type, will people be able to see? Or if I go to everyone, why should we care about storytelling in mathematics? Is that something that most people can see? Okay. So does anyone have any thoughts, any suggestions about this? Okay, can humanize mathematics, can make it relatable. Math is a human endeavor. Okay, very practical. It helps make things understandable. Provide a signal, can be inspiring. Okay, so I think that a lot of us are on the same page. We had a note about how we can hear about diverse experiences, and these can encourage students. We want to know about the greater world of mathematics. So one immediate thought, and I think this is sort of echoed in the comments, is that storytelling can help us humanize mathematics. It can help us communicate mathematics more effectively. It can help us connect to mathematics, and it can help students and ourselves value mathematics. So for me, at least, my experience learning mathematics is that it was sort of presented as a collection of maybe eternal truths. There are a lot of objective algorithms. Things just were. So it's very formulaic discipline. And I did love it. I love the numbers. But I recognize that maybe outside of a history of math class, there's very little regard given to, the larger social and cultural environments that support and sustain mathematical communities. And I believe that this is one, certainly not the only, but one of the reasons that a lot of people feel isolated or disconnected from mathematics, right? And so if we use storytelling, right, as a vehicle, it can help us contextualize the math that we learned, and it can also serve to increase access. And this lies into this idea of whose stories are we telling, right? This can help us reshape our perceptions of who can be a mathematician. So when we talk about storytelling, so there's a traditional sense, right? Like, what do we mean by a story? It has to have certain things. A story has to have a setting. We need some sense of time and place. We need characters, who's the protagonist, who's the antagonist. We need a plot that moves forward. We need a theme. What are we supposed to take from this story? And there's, other things that I've listed below: a narrative arc, a message, a conflict. There are a lot of different elements of storytelling, but they're sort of agreed upon that the more of these elements and the more fleshed out they are, the better the story, right? So when we think about this mathematically, I wanted to talk about the stories that I like to tell. And I think that I try to be as intentional as possible about having 4 key components to these stories. So the first is the math, right? We're mathematicians, we're interested in learning mathematics. So the math, we want to be central in the stories that we tell. And I don't think that as a community, we have a problem with this. We want to center the math. It's our natural leaning. So this second part is thinking about the individual, right? Who is doing the math, right? Who or what small groups are doing the math that we think about? And so putting these 2 things together will get you an okay story, right? You might get a name theorem and maybe sort of a tidbit in class about where this comes from. But this math and the individual who does it is something that I think we do an okay job of as a community. It's these third and fourth parts that I think can really enhance the mathematical stories that we tell and that are often missing. So by community, what I mean are, the groups and the situations in which we find ourselves doing mathematics. So who are our mentors? What settings or what communities are we a part of? So this is taking place during an ICERM program called Girls Get Math. That program is a community of women learning mathematics, right? And I'm a part of a community called EDGE, right? And there's so many other little communities that I've been a part of along the way. But what we don't often think about is how access to those communities can help us learn mathematically, can help us grow, but can also sort of serve to help or hinder our experiences in the discipline. And this last part is a society, right? Math doesn't exist independent of society that we live in. And in many cases, 4 and 1 work together very well. So we have society, and it influences the type of math that we do, the type of research that's prioritized. It influences the type of communities that we have access to. And so all 4 of these things, what I'm trying to say is that they all work together to form a really good mathematical story. And then a last example about society shaping math. We are in an era where we have access to large amounts of data, and we need to learn how to access it, how to process that. And so we see a lot of mathematicians who are trying to learn new techniques to do so. So this is an example of society, influencing the math. But all these 4 things together are what I say make up a good mathematical story. So when I think about mathematical stories in terms of teaching, right, I think that when we think about hidden narratives in the way that I'm defining them are stories from those who are not already sort of amplified and celebrated in our history books, which in math is a great thing because there's very few people who we celebrate. And so there's so much room for telling stories of people whose work has not been highlighted or amplified in our mathematical communities, right? And so I think for me personally, you know, this focus on highlighting hidden narratives has centered around telling the stories of Black mathematicians. But I think this is something that I've chosen to do, but I think amplifying the work and contributions of anyone who's minoritized in the discipline helps to highlight different pathways to math. And I also think it helps to get at this different piece, which is, you know, how do we investigate how community and society influences the math and the people who see themselves doing it? And so how does this show up in my teaching? So one of the stories that has influenced me the most in terms of thinking about society and culture and community and different individuals and really cool mathematics is the Hidden Figures story. And so this story is based on a text by Margot Shetterly, and it is titled Hidden Figures, The American Dream and the Untold Story of the African-American Women Who Helped Win the Space Race. So it's the title is very descriptive. And so when this movie came out, the book was later turned into a film, a lot of people were extremely inspired by these stories because here we are telling a story about math, about how different people overcame obstacles to contribute to mathematical discipline in a really profound way. And so when I heard about this story as a graduate student, I knew that as soon as I got the chance, I wanted to try to find a way to teach it. And on this slide, I've included one of my favorite quotes from the epilogue of this text by Margot Shetterly, which is basically saying that this story was really electrifying for many reasons. But for one reason in particular, it's showing that, for example, Black women, we can see ourselves as protagonists in the story of America and not sidelined. And I think that this is one of the goals of amplifying hidden narratives, is who is sidelined in the stories that we tell and who do we amplify. So I want to highlight some of the stories and some of the neat math that I learned along the way of sort of unpacking this Hidden Figures story as an instructor. So the first, and I'm calling this a hidden figure. And so I want to talk briefly about Eunice Smith. So the hidden figures were human computers. And so before a computer was, you know, a Mac or whatever you may think of it now, it was a person. And so in the early days of the space program, the National Aeronautics, oh gosh, it's NACA, but I always switch around the acronym. So I won't do it tonight. But the idea is that these women came to Langley Research Center, right, to have a possibility to have a career as a mathematician. And so Eunice Smith is not featured in the film. She's featured in the book, and in a tangential way, she's described as Katherine Johnson's best friend. So I would say that Katherine Johnson is sort of noted as the heroine of the Hidden Figures text, and Eunice Smith was noted as her best friend. They did community service together, they wrote to work together, but when we're doing research for our class, we noticed that she had an entire story on her own. So she was somewhat hidden, even amongst the hidden figures. And so she was born in 1923. She was the youngest of 7 children and was a native of Virginia. And so she went not too far from home, about 30 minutes, to Hampton Institute. This is now Hampton University. This is a historically Black college, and she earned a bachelor's degree in mathematics. And from there, she was recruited and began to work at NACA, as one of the very first West Computers. So the West Computers was a segregated computing group, because at that time, they also had white female computers and Black female computers, and they worked separately. So the West Computers were the Black female computers, and the East Computing Group were the white female computers. And as you see in this image, they often worked together, even though they had separated facilities. So this image is from later on in Eunice Smith's career. This is an example. She's here on the far right. I hope you can see sort of my green dot over her. And after she published 6 research reports, she was very active in the Federal Women's Program, which was aimed to try to increase opportunities for women inside of Langley Research Center. And so she passed away in 2006, but by going through her story, I learned more about the programs and initiatives that women took, Black and white, within Langley to try to advocate for themselves within the workplace. I learned about her research in ground loads engineering, which was very interesting, in aeronautics. And I also learned about the mathematical tools that she and the other human computers used. And one of those was a slide rule. And I became very fond of those. And I wanted to share just a little bit about what I learned. So I'm not sure if you are familiar with slide rules. I'm going to type another in the chat. Has anyone seen one of these before? And that's supposed to be a question mark. Okay, so I see Dr. Hassett. Okay, someone says I have one. Okay, great. Oh, a collection. So the interesting thing is that I actually was, me and my colleague, John Johnson, we actually went to someone's home 2 weeks ago who had a private collection of, there were thousands of rules at that home in the basement. It was really cool. We're not quite sure what we're going to do with it in terms of like trying to use some of those for our class. But the point is, they're a really cool instrument. And so they were first built in the 1600s. And they were based on John Napier's discovery of logarithms. And what this is this mechanical device. It was used by human computers, engineers, and astronauts at Langley Research Center. But even if you were just a student during this time period, pre-1970s, then this was sort of your standard. So in the same way that, you may have a TI 80 or just a TI or HP calculator these days, Casio, back in the day, and I say back in the day, decades ago, you might have used a slide rule. And so the reason that you may not have ever seen one is that in 1972, Hewlett-Packard came out with the first handheld electronic calculator. And almost overnight, these made slide rules obsolete, right? And so now all of a sudden, you have something that's very small that you can kind of carry in your pocket, even though there were pocket slide rules, but it was electronic. And so the slide rule is a very physical, manipulative device. And it's very difficult to use without understanding what you're doing, unlike the calculator that you can use without any prior knowledge of how the calculator works. So I want to do a small demonstration. So I'm going to stop my share. And earlier, so I have two things ready to go. I have a virtual slide rule that I actually want to share in the chat so that everyone can sort of see an example of how you might use this digitally. But here's a link to a virtual slide rule. I will try one more time to see if I can share my screen. And it looks as if it's not working. So unfortunately, you will not be able to see me model on my actual slide rule, but I will model for you virtually and just talk a little bit through how these work. This is heartbreaking. It worked earlier today. Okay, so let's share screen. Okay, so if you have this pulled up virtually, I just wanted to talk a little bit about how these work. So I moved this to short long, and this is what got it on one side of the screen. Okay, so I just wanted to talk a little bit about what this is. So you can see this if you're looking at my camera in person. This is what this slide rule looks like, but you can have this virtually, and it's just as good as the real thing. So the slide rule consists of 3 parts. And so if you can see where my mouse is hovering here, we call this the body of the slide rule. Okay, and then the middle part is what we call the slide. And so the middle part moves, it slides and grooves within the body. And you can move that virtually. And then we have a cursor. And the cursor is this gray part, and it has in the middle of it what's called the hairline. So what about these markings? So the scales on the slide rule appear on the left-hand side of the rule on the front and the back. So right now we're looking at the front. If I clicked on this, you would see that we can also look at the back. Okay, and so this particular slide rule is a post-1460 Versalog. So this was an industry standard for engineering students. It's very likely that they may have used these or variations of these at NACA. I'm saying NACA because this predated NASA. And you can't tell, but it's this sort of pale yellow color. And that's because it's made out of a laminated bamboo. So the bamboo is for a durable construction, but the laminate, you can't tell because you can't feel it like I can feel mine, but it's coated with a thin layer of plastic. And so this helps ensure against warping, and it helps the rule operate smoothly over different weather conditions. So the letters that you see to the left here are scales. And each scale sort of helps you solve a different arithmetical problem, except for addition and subtraction. And all of the scales, except for the L scale here, are logarithmic. And so this means that the distance along the scales are proportional to the logarithms of the numbers that you see here. And so this is why, if we look very closely, I'm going to look at the C scale here, where my mouse is hovering. If we look, then we start at 1, and we go about this far to get to 2, a little bit further to get to 3. But if you notice, the distances along the scale are getting closer and closer together because it's a logarithmic scale. And there are scale equations that can help you determine how far the distance needs to be depending on the size of your rule. But the two scales that are used the most often are the C and the D scale. So if we go back, if you look at my mouse, the C scale is, can you all see my mouse? Can somebody like nod? You can't, can you see where my mouse is doing?
Yes.
Okay, great. So the C scale and the D scale are two of the most commonly used scales. And so they appear twice and they're the same. So if you look at the C scale and the D scale, they're exactly the same, except for the C scale is on the rule, so we can move with it, and the D scale is not. So I want to talk about how you could read these scales. So let's look at this mark right here. I'm going to move the hairline so that you can see, and this is 1.3. And so what I'm doing is I'm hovering 1.3 over the C scale. And since you're on the computer, you can press this box at the top hand corner that says markings on the center line, and this will let you know how close you're getting to where you want to be. Okay, so this says 1.3, but it could also represent 0.13. It could represent 13. It could represent 130, or any number with the figures 1, 3, no matter where the decimal point is located. And so a similar statement can be made for anything along these other tenths marks. If we look about what's happening between 1 and 2, it's subdivided into 10 parts. And so we even get a notion of hundredths, right? However, if we look at what's happening from 2 to 4, there's only 5 spaces between the tenths as opposed to 10 here. There's now only 5, so we read this as kind of like 0.2, 0.4, 0.6, etc. And then from 4 to 10, we see there's only 1 mark between tenths. So you have to do a little bit more estimating there. And so any mark is going to represent many different numbers that have the same number of digits. So let's talk about how to do something simple like multiply. So I'm going to start with 2 times 3 just to, humor everyone. So, okay, so to do this, what you do is if I want to use the C and D scales to multiply, I'm going to start with the index on the C scale. The index is this 1 here. And I'm going to move it so that it aligns with the 2 on the D scale. So now it's aligned, okay? So 2. And now I'm multiplying 2 times 3. So I'm going to move my hairline to the 3 on the C scale. And when I look down, I should be able to read the product, right? I should be able to see 6. So this is telling me that 2 times 3 is equal to 6. And let's see, does anyone want to give me another example? Maybe this is risky, asking just 2 numbers. Risky asking live. I have like my pre-made examples already. 2.7, 3.1. How about 2.7 times, well, we just did 2 and 3. Okay, so let's do 2.7 times 18. I'm just gonna switch it, or we could do 31, but I wanna move a little bit. So if we do 2.7, so we're gonna start over. Okay, and I'm going to move the index on the C scale to 2.7. So I'm at 2, 2.1, 2.2, 3, 4, 5, 6, 7. So if you see, I'm really close to E, right? And that should make sense. This tells us we're in the right place. And now I want to multiply by 18. And so this is where we have to think about how decimals work. There is no 18. The rule only goes from 1 to 10. And so we're going to go to 1.8. because remember, this is going to represent anything with the figures 1 and 8. So we're at 1.8 here, and then we simply look down on the D scale. And so, this looks like, let's see, it looks really close to, so it's 4.95. Did someone actually do this in real life? So I'm saying 4.95, but what's wrong, right? I'm doing 18 times 2.7. So how many digits should my answer have? Like, where should the decimal be? Instead of 4.95, what should my actual answer be? Yeah, 49.5. And I'm not sure if it is 1.8 times. Was I close? I actually didn't compute this. What is 18 times 2.7? $48.6. Okay, so it looks like maybe, okay, so yeah, if I go back, I can see that I was a little over with my cursor, but I want to talk about some of the things that just happened. One, we had to figure out how many decimal places to use. So I saw different kind of reasonings throughout the chat. Someone said we need to multiply by 10, so we could think of this as maybe, just really naively, we could say 20 times 3 is 60. So I know I maybe need 2 digits. That's one way to think about it. There's a lot of different ways. And so you have to actually understand where to place the decimal when you're doing these computations. You also have to be able to read the markings on the rule to see, are we in the hundreds place? Are we in the tenths? You have to learn how to interpolate between the readings. And so if you imagine using this, right, there's no way that you can use it without actually understanding what's happening. And so what's so fascinating to me is that these human computers, these women, and also these engineers, they use this technology to build our space program, right? Eventually computers came along and they were wonderful, but before that, we had slide rules. And so, so someone said you really need some good glasses. So you can find these used on eBay, sometimes brand new, because like I said, whenever the new calculators came out, they sort of essentially stopped processing these. And because of that, you can find many new boxes of slide rules just completely brand new and unopened. And there are also a lot of collectors. So for our course, we went through the International Slide Rule Museum, and they were able to send us a loaner set. They send loaner sets to institutions who would like to use these in their classes. So I want to talk just briefly a little bit about some really basic math concepts that are happening here. So I'll stop sharing this screen and go back to my original presentation. So I wanted to make a quick note just about why the slide rules, if you're still looking at yours virtually, about why you have different distances between the numbers on the rule. So each slide rule is going to come with a scale equation that's going to let you know how far each distance should be from the index. So this is kind of known, the Versalog is known as a 10-inch rule. And so it uses this scale equation that you see above. So it's not quite 10 inches, but this means that the entire length of the rule is 9.84 inches. And because there's a curve here, rather than a straight line, this is indicating that you're not going to have evenly spaced indices along your rule. Another thing to note is that when we're doing multiplication, this is a really great way to highlight logarithm rules in action. So when I learned about logarithms, I kind of just memorized the rules. To be honest, I remember that there were graphs that helped me understand what was happening. But I think having this physical manipulative is really insightful to see what's happening here. So when we did, we chose 2 times 3, but here's just an example written out of 2 times 4. What we're really doing is adding the length that represents log 2 and the length that represents log 4 base 10. And so the sum of those lengths, right, is going to tell us what we want, which is the product of 2 and 4. So I think that this is a really neat thing and neat device. And I think it's a really great physical manipulative if you're interested in using it for teaching. So here's some of the math, right? Getting back to what we talked about with mathematical stories. I talked about an individual person, Eunice Smith, I wanted to talk a little bit about the math and the mathematical tools that these individuals used. And I next wanted to sort of talk about how we tied that into the classroom.
Ranthony, there's a hand raised. I didn't know if we could take a question.
Yeah.
Alexis, can you put it in the chat? Okay, the hand's gone down, so I'm not sure.
Okay.
All right, just put it in the chat if it comes back. Thanks.
Okay, great. So when we did this in the class, we talked about slide rules as a tool, right, that was used by these human computers. And then we used the hidden figures story to talk about pathways to STEM and sort of intersections of math and society. And one way that we sort of allowed this to trickle into the local community was to ask the same question, but for individuals around Columbus. So if I'm a math major and I'm interested in what I can do with my career, if for some chance I don't want to go to graduate school and become my professor, what are my options, right? And thinking about those options, what kind of tools do people use, you know, in their mathematical careers? Are there any that are similar to the slide rule that we just talked about? So what we had our students do was to sort of interview what we call local hidden figures. And so just briefly, this is Lynette Campbell. She is a engineer at Honda Manufacturing, which is located in Marysville, Ohio. And she, when we talk about community, right? So she is someone who's a part of a engineering fraternal organization. She's someone who went to a historically Black college. And so she talked a lot to our students about transitioning from an HBCU to a predominantly white institution when she went to graduate school. She also talked about advocating for more women in engineering. And then she talked about what inspired her to do math, right? This is Dr. Frederick Bertley. He's the CEO of COSI. This is a science museum here in Columbus, Ohio. And he's a mathematician in training as an undergraduate who is now directing a science museum. So he went on and got a PhD in immunology and did a lot of really impressive medical work before he came to Columbus. Are we supposed to be seeing people? Can you see now? Okay, so this was Lynette Campbell. And this is Dr. Frederick Bertley. And then this is Dr. Sybil Brown. So she is a high school teacher. She used to be the high school STEM coordinator for Columbus City Schools. She runs a robotics club. She does a really great job of introducing students to advanced mathematics as an after school activity. This is Lauren Burke. She does a lot of great work with women in data analytics. She's very passionate about getting more women experience with coding and with software and technology and data science. This is Dr. Kenny Salau, and he is someone who went through the traditional academic pipeline all the way to doing a second postdoc, and now he is transitioning into a career as a data scientist at JP Morgan Chase. And this is Dr. Gerald Carter. He's an assistant professor at Ohio State, and he uses mathematics to study social networks, and he runs a lab that studies bats and behavior. And so what you see here is sort of a hodgepodge of different mathematical stories. So we have sort of these historical stories that we talk about with the hidden figures, but then there's also these contemporary stories, modern people in our communities who are doing mathematics and who are talking about the communities they were a part of, the mentors that they had, how society was when they were learning, you know, in addition to the math that they do and who they are as people. And so all four of these elements are being present in the stories that they're telling to our students. And the last thing that we did was we had our students tell their own stories. So this is just a small sampling, but these are students who are reflecting after talking to modern hidden figures, after learning about historical hidden figures. They're using these narratives to do kind of what we were talking about earlier in the talk. They are thinking about their place in the mathematical community, about how they can make the math community better. And they're also thinking about, you know, their pathways up to this point and what they might want to do to help them change. Just sort of a reflection is that this idea of looking at stories is universal. And everyone has a math story. I have a math story. I haven't shared it yet during this talk, but here are some of the reflection questions that we gave our students as they were thinking about theirs. So when we think about what mathematical communities that we belong to, this is very broad. We could be talking about the research communities that you're a part of. We could be talking about the informal networks that you're a part of, the professional societies, the clubs, the organizations, the summer camps, right? So there are so many different ways to interpret what a math community is, but this idea of communities and mentors playing a pivotal role and sort of the pathways of different mathematics professionals is this recurring theme that we see by looking at narratives, right? Because we're moving beyond just the person and the individual and thinking about their story comprehensively and holistically. And so here are just some examples of reflection questions that you may want to ask if you're interested in, thinking about and reflecting on your own mathematical story in preparation for helping your students. So this is sort of the first close of a thought. And so I wanted to talk a little bit about hidden narratives and how they've shown up in my teaching. And the next I wanted to talk about hidden narratives and how they've shown up in some of my more recent research projects. So I actually want to pause and ask if there's any questions up to this point before we sort of shift gears a bit. Okay, so I don't see any. I did the long online pause. Oh, what class were the student reflections made in? So this is a course called, the course is Math 2010S at Ohio State. It's called Intersections of Mathematics and Society. And it's a class that is open to all undergraduate students. We had, the first time we ran it, we had a mix of we had 2 math majors and 2, like 1 data science major and another engineering. But the last time we ran it over COVID, we had like a communications major, an architecture major, et cetera. And so it's really meant to be for students who maybe aren't math majors. So we're aiming it at freshman, sophomore level students. So they're not all planning to major in math, because we feel that even if you're not going to become a professional mathematician, there's a book by Francis Zhu, I think many of us may be familiar with, and he talks about humanity and mathematics and how we're all teachers of mathematics, and we're communicating ideas and attitudes about mathematics in everything that we do, and we're teaching those to the people around us. So even if these individuals aren't going on to become professional mathematicians, they're still teaching what math is to the people around them. And I think this class helps them get a very different idea of what that can be. And this is a general education required. So it's a gen ed in our College of Arts and Sciences. It does not currently count for the math major or minor at our institution. And let's see. And then I got a question, what's my mathematical stories? Who are my mentors? So that's a long, nuanced one. And maybe I will say that one for the end. Okay, so I'm going to shift gears to just talk about why the sort of the motivation for this newer research project that I'm doing. So last summer, this is a picture from George Floyd protest in downtown Columbus, Ohio, in the summer of 2020. And so the reason that I'm starting here is because this is sort of where my more recent project looking into Black math history began. And so this is actually an image that was taken that my husband took. His name is Joshua Edmonds. He was a very gifted photographer. And this actually became a part of an exhibit of protest photography a couple of months after the protest that summer. And I remember going out there. It took a while. He went out every day for weeks, and it took me a while because I didn't know what to do and I didn't know what to say. And I remember sitting here and thinking, what can I do? Like, I know that I'm doing a lot, right? I know I have this course, but I really was curious, what can I do that sort of feels like it's in my lane? How can I use storytelling to address racial justice in mathematics? And what would that even look like? And so what ended up happening is that I became very interested in sort of just the history of the institutions that I've been a part of. So when I first started this position at Ohio State, one of the first things I was told is that you were the first Black female postdoc that the department has ever hired. I don't know if this is true, but it was ringing in my ears. Was I really the first, and will I be the only? And I was thinking about this during these protests, and I was really reflecting on it. Is there a way that I can use the things that I'm comfortable with, storytelling, to approach racial justice in mathematics? And I started reflecting on the following questions. If I'm really the first or one of very few, like what historical factors have contributed to this? So in the Hidden Figures class, we talked a lot about how a whole host of things led to the opportunities that the women and the human computers had at Langley Research Center. So what sort of historical factors have contributed to this lack of representation? It had to be more nuanced than people are mean and no one's given chances, right? What's actually happening? And I was really curious about, well, if this is really true, if I really am the only one coming in as a professional, what about students? You know, how have minoritized mathematicians been served by institutions historically? And, you know, in the same way that we looked at local hidden figures for our course, what stories can we tell from our local communities that can help us illuminate the questions that I've listed here? So the first thing is that I recognized that I was not the only, y'all. I was like, okay, here is Rada Higgins McCready. And so she is actually the 20th Black woman in the world to earn a PhD in mathematics. She earned her PhD in mathematics in 1974 from Ohio State. And she is here in this really smart, sharp polka dot dress that you see in the front row. And the thing that's interesting about her, and the reason that I connected to her story, is that she grew up in Columbus, Ohio. She was local. She went to, she went to Columbus City Schools. I'm forgetting the name right off the top of my head. But she was someone who was sort of hand discovered by someone named Arnold Ross. And when I began my position at Ohio State, I started as a Ross assistant professor. So Arnold Ross is a former department chair, a really well-renowned math educator. And he was very, very focused on advocating and finding local mathematical talent in somewhat hidden places. And so he started this Ross mathematics program that you see photographed here. Here are participants. It's still running today. And there's been derivatives of this program in other places across the country. But he sort of hand-selected Rada Higgins to participate and sort of helped her begin this trajectory to become a professional mathematician. And the second person that I learned about that I found really fascinating was William McWhorter. And so as you see, I see Ohio math history because this is just not about Ohio State. He's a native of Cleveland, and he attended public high school there. He attended Ohio State as an undergraduate and as a graduate student. So both of these individuals, Rada Higgins in particular benefited from an NSF fellowship, which was a direct result of sort of increased funding during the space race period. So she was also influenced in part of this sort of period in which we find ourselves thinking about the hidden figure story. But when I got into William McWhorter, I found some really interesting mathematical ideas. So I want to be cognizant of time, and so I'll sort of just briefly talk about some of them. The first is that I found that he was a really renowned fractal theorist. So what I've done is actually pulled quotes that someone wrote in his obituary online. And essentially what they're saying is that he was an outstanding fractal theorist, and he was even called the first American fractist. But they noted that he was Black in a generation where he was rare in the discipline. And there's not a direct correlation, but there's a note that they wished it hadn't been so hard for him to publish, and that the world would have been served by seeing his work. And so he was really praised by this particular colleague. And this sort of gets into the idea of whose narratives do we amplify, and how does this contribute to our perceptions of who has done what in the discipline. And so in particular, Dr. McWhorter was a really interesting person. So in terms of his work in fractal theory, I think I will maybe bypass a bit of the background about sort of what they are, but the idea is that a fractal is a shape. And it's a geometric object, but kind of like a point or a line or a plane. But unlike sort of the familiar shapes that we know, they have a complexity that you can't really measure conventionally. And you can't actually draw a fractal, but you can approximate it. And so one thing I wanted to highlight is this idea of self-similarity. And it's the idea that a shape can be made of smaller copies of itself. And before 1980, so he earned his PhD in 1963. So during his career, fractals were hot. They were new and they were sort of on the scene. And so there's not a lot of attribution to those who sort of studied before Mandelbrot, before that he was sort of a before and after point in the development of fractal theory. And so here's an example of a Sierpinski triangle. It exhibits self-similarity. So, you know, we could take this triangle, we could decompose it into three congruent figures like here, here, and here. and each is going to be exactly half the size of the figure we started with, and so on and so forth. And so I do have an image, but once again, I think I'm going to maybe bypass this one in favor of talking more about dragon curves, which is what William McWhorter was really interested in. And so this is a quote from an article that he wrote in a magazine called Byte, and that's actually the first link that I sent by accident when I was trying to find the slide rule. So it takes a bit to load, but if you look, it's on page 123 to 132 of that long PDF. And basically, he was saying that seeing a completed dragon can't compare to the thrill of watching it being drawn. So he's really, in the way that he describes these, he sees them as sort of like really fun objects. And so when we think about a dragon, it's named after John Highway, who is a NASA physicist. And it's basically constructed, you can't see the original line segment, unfortunately it got cut off, but you repeatedly replace each line segment by two segments with a right angle and with a rotation of 45 degrees to the right and left. And so you continue doing this for several iterations, and you end up getting something that looks like a dragon, so to speak. And so I did want to show just an example of sort of what this looks like when it's unfolding. Okay, so we're starting with a baseline segment here, and then we're replacing that baseline segment with two segments with a right angle and a rotation of 45 degrees, alternating to the right and to the left. And so this is an example of similarity. We're repeating the same pattern, except it's being tilted by 45 degrees and being scaled by a ratio of, I think, radical 2. So this is an example of sort of how you might iterate a fractal, and what each time you see it building upon itself. Dr. McWhorter called this a day of life. So he considered something to be the birth, and then day 1, day 2, day 3, etc. And so he saw these patterns as sort of being thought of as like the DNA of a fractal. And he was really interested in figuring out little tiny tweaks that you can make to the DNA of a fractal. So if you instead of a line, maybe you start off with a different type of curve. Maybe instead of 45 degrees, you move to maybe, 72 or 36. Like, how do these different things influence the fractal that you end up with? So he was really interested in finding the variations of what's called a dragon, which is what you see here. And I just thought this animation was really great. And I wanted to share it with you guys.
Thanks very much. So are there any questions or comments? So if you, I don't think that we can have people give them directly, but if you include a question in the chat, I will happily read it until Ranthony gets tired at least.
Yeah, so
see lots of kind words and
I wanted to, do you mind if I sort of just briefly move to the end of the,
go ahead.
So,
yeah. Mm-hmm.
Yeah, so what I'll do is this, because I want to be respectful of time. So I'm going to actually share the link to my presentation into the chat, so that everyone can kind of see the things and where we're moving. So I got a little caught up on the slide rules, but the last thing that I wanted to mention is that I am really interested in exploring the sort of the math that we continue to unpack and find by looking into what I'm calling, like hidden figures from the Ohio State University. So in addition to looking and learning about fractal theory, going into Dr. McWhorter's work, I learned that he came up with an algorithm for computing the characteristic polynomial of a square matrix with row entries without determinants. He was part of a group of mathematicians who wanted to contribute to the dearth of the determinant. This was along with other popular names like Sheldon Axler, and he just didn't believe that it was computationally necessary at the level of most undergraduate courses. And so he actually used to teach the undergraduate honors course here, and he used these techniques. And so we're hoping to, when I say we, a group of students are hoping to sort of go through this paper, unpack the algorithm, and develop a lesson plan that we can put back into the honors course here, along with sort of a bio of who he was and what it was like when he was studying mathematics at Ohio State. And so what I'm continuing to do is to look at these four things, right? Community, society, math, and individuals, but in the context of alumni from Ohio State. And we've learned some really interesting things so far. We've learned that there are exactly 8 or 7 PhDs that identify as Black that have graduated from Ohio State, all between 1963 and 1984. And there are a lot of really interesting things happening during this time period, a lot of really interesting shakeups in department leadership, protests on campus, et cetera. It was a really interesting time. And so, trying to understand what contributed to that cutoff in 1984 for there to not be any Black PhDs since, and looking at the effect of, selective admissions. Ohio State used to be an open enrollment sort of institution. They switched to selective admissions. There's a lot of things that we're looking into, but we're learning so much math along the way, and we're learning so many interesting stories. And a lot of them are very local, just to Ohio. And so we're really hoping to share these stories with people whose schools that these individuals came from, graduated from in the community. I think the main thing that I want to iterate is that when you're telling mathematical stories, it doesn't have to be divorced from the mathematics. That in fact, this idea of storytelling and this idea of looking at math and the people and the society that influence it is part of what it means to be a mathematician. And if nothing else, I hope that you remember this. And if you find yourself discouraged, you belong here. And if and when you decide to join the mathematical community, we will be here with open arms.
So one question that I think many of the Girls Get Math audience might be curious is, what is your story like? What got you into mathematics? And was there a spark? Was there a mentor? Was there like a little story that got you involved? The first day, Professor Ott went and had everyone tell their stories about what was the sort of thing that got them excited. And maybe we could, if you would be willing, maybe you could say a little bit about your story.
Yeah, so I actually, I say that my story is unconventional because I came from a performing arts background when I was younger. So I didn't really participate in mathematical enrichment. I was a creative writing major at a school called SCAPA, which is the School for the Creative and Performing Arts. So this idea of storytelling is sort of innate to me. It's been a part of me since I was younger. I've always enjoyed math. I enjoyed puzzles. But when I was in high school, I participated in a magnet program for, I guess, gifted students, and it did not go very well. I mean, part of it was I was an emotional teenager, right? I had a lot of feelings, but I just did not adjust to the setting, to my classmates, to the program. And so I got dismissed for getting a C in statistics and a C in chemistry. And so I just assumed, well, I guess that's it. I really like math, but this is telling me that I'm not good enough, so I should probably just quit. So I continued, to take math courses. But when I started college, I was a pre-med major. And eventually I became English pre-med. And as a pre-med major, you have to take biology, calculus for biology majors. And so I took that course and I started tutoring it. And I got to a point, maybe my junior year of college, where I realized that tutoring this class was the highlight of my week. So as a junior, second semester, I switched to my math major and I took calculus 1. Again, for math majors this time. And so I started off a bit late, right? Declaring my major as a second semester junior. I had to go an extra year of undergrad. When I got to graduate school, eventually, I had no idea that there were such thing as RAUs. I got into one graduate school. And I think that's when I really started to form communities. So I would participate in the EDGE program. And that really helped me. It was the first time I had done math with other people, other women specifically. I started going to conferences and I realized that other Black mathematicians just existed. I didn't know that that was a thing. And I also participated in the Math Alliance, and it was just really crucial because I got that mentoring that I had never had. And so I think there's a lot of things, even when I got to my postdoc, there's so many things at each layer that I realized I just didn't know because I was sort of operating on the outside of different sort of insular mathematical communities. And that's okay, because I've made it work anyway. But I think the thing is that my story is really unique in that I sort of operated outside of the bubble. It also means that a lot of the values that exist inside of a more insular community that I never adopted as my own. And I think in some ways that's a good thing, because those can be a bit limiting. So I just really appreciate opportunities to come and talk about this. Like, for instance, Dr. Ott was a postdoc at the University of Kentucky when I was there, sort of floundering as an undergraduate major, trying to figure it out, and was always very helpful. So yeah, my story was I was really into storytelling, and I sort of saw math as like logical poetry. I just thought that it was beautiful, and I wanted to learn as much as I could. But I need a lot of help at each phase, trying to figure out how to get me where I wanted to be. A lot of failures along the way. I'll just end with a shameless plug. So the project that I mentioned about looking at Black math history was actually funded by a C grant for racial justice here at Ohio State for around $50,000. And so we're going to be creating a digital site of Black math history from Ohio State. And of course, it's going to be intimately linked with the history of the state of Ohio. And so we can't wait to share this. Probably will be up and out at the end of the upcoming academic year. But we're really excited to share this so that, and we anticipate having a lot of resources for teachers. And we're talking with local teachers about what they may need so that they can share these and bring these stories into the classroom.
Okay, well, thank you so much. It really is a wonderful story and wonderful to hear all the stories. I think I have to clap because I'm the only one that can be heard. So let me clap for all the other 100 people who enjoyed this talk. So thank you all. Stay tuned. We have other lectures coming up. I think in September 22nd, we'll have a lecture by Daniela Witten, if I remember correctly. So stay tuned, take care, and be in touch. Thanks all. And thank you very much, Katie, for helping to bring this about.
My pleasure.
Okay. Good night, everyone.
Good night.